Hello everybody. We are going to do our midterm 2 review here for oceanography, so hope you're ready. Hopefully we'll be able to get through this in less than an hour, that's what I hope. There's only 60 questions on here. I know that sounds like a lot, but it's a lot less than the last midterm review, so that's a good thing. We're going to go through these right now without any further ado, so bear with me. What are the three basic subatomic particles? So of course you know this is starting with our ocean water structure and getting ready also for the chemistry. You know that's probably the proton, neutron, and electron, of course. And you should also know the charges on those, right? That's a plus for the protons, neutral for neutrons, and electrons are negative, okay? Now you should be able to kind of draw out a model. You're not going to have to do this on the exam, but you should know how they're kind of arranged within an atom. So, you know, the protons and the neutrons are in the nucleus, and of course the electrons, they are going to orbit in discrete shells around the nucleus. And I shouldn't say orbit like planets, but they, let's say, occupy discrete shells that are certain distances, average distances away from that nucleus, okay? Now, how many orbitals, how many electrons fit in that first shell? So the first shell, there are only two. So you can only have a maximum of 2 electrons per the first shell. That goes back to something called Pauli's exclusion principle, which of course you would learn about if you were taking a chemistry class. But you know, that's the only number of electrons you can have in the first shell. Subsequent shells after that can have up to 8. So you can have them like this, kind of 1, 2, 1, 2, 1, 2. They usually do kind of pair up this way to balance out the spins. One spins one way, the other spins the other way, and it helps to stabilize the atom. So anyway, they can have up to 8 in subsequent shells. In reality, it's actually a lot more complicated than that. You can have shells with 14 or 10, but we don't really care about those kinds of elements in oceanography. So for this class, it's fine to just think of it as 8 for the second shell. So you want to put 2 in here, 8 in the next shell, okay? And then you can have subsequent shells, right? You can get even larger and have even more shells, and those will have, you know, 8 in them. So just, I don't have enough space to draw it all, but it goes like that. So atoms are most stable when their outermost shells are full, okay? So we do recognize that bonding between atoms is a function of electrons trying to get their outermost shell filled. So that's what atoms are trying to achieve. They become most stable when they are filled in that way. So they're always trying to get that outermost shell filled, okay? Now, to do that, they will often ionize and bond with other atoms. So that process of ionization is just when you have an electron take on an atom take on a net charge. So atoms become ions, right? That's ionization. Is atoms become ions. That means they take on a net charge. So that means they're either going to gain or lose electrons, right? By gaining electrons, they're going to take on a negative charge and become anions, okay? So anions have a negative charge. I'm going to put a negative there. Cations have a positive charge, okay, like that. So anions have a negative charge. That means they've gained too many electrons, more than their protons. And then the cations is when they have lost electrons. So now they have less electrons than their number of protons, and they've taken on a net charge, okay? So ions, again, just means that they are atoms with a net charge, either positive or negative. You know, anions, negative, cations, positive, okay? Now, for ionic bonds are just bonds between ions, right? So they're bonds between ions. Whereas covalent bonds are bonds that involve, and I should say one thing here, this is when basically atoms bond by taking or giving electrons. Okay, so I'll just put an E negative right there. That's kind of the common sign for an electron. So they're either taking electrons or they're giving electrons away. And that's how they balance out and have that full outermost shell, okay? Now, another way that atoms can bond to get that final goal of having a full outermost shell is by sharing electrons. So covalent bonds occur when electrons are shared among different bonding partners, okay, different atoms. Now, you should know that water molecules, H2O, right? oxygen, you have the other hydrogen here, sorry, another hydrogen. Those are covalent bonds. So the bonds that are drawing together the hydrogen with the oxygen, those are covalent. Okay. Now, why do water molecules have that angular structure instead of a straight line structure? So you should have a little bit of familiarity with this. This could be a short answer question, so you should have a little bit of familiarity how to explain this. I'm going to give myself a little bit more room here just so I can explain it more. But basically it goes like this. If you look at oxygen, okay, oxygen is element number 6. So it's element 6. And it's going to have, I'm sorry, I'm not thinking right. It's element 8, carbon 6. It's element number 8. What I actually meant to say is that there are 6 electrons at outermost shell. So the first shell of oxygen is going to have, the 2 electrons. That outermost shell is going to have 6. And like I said, electrons really prefer to split up into pairs. Okay, so you're going to have pair 1, that's 2, and then another like this, and then you're going to have 2 that are by themselves, okay? So you're going to have these 2 sort of unbonded, unpaired electrons, okay? And then that ends up with 6, right? So you see 1, 2, 3, 4, 5, 6. So what's going to happen is these are going to bond with the hydrogens that have 1, right? They have 1 electron. And this is going to bond with the other hydrogen that has, again, 1 electron. Now, if you actually think about this, actually, let me get kind of a model. Might help you imagine this, and I can kind of show you a little bit better why the geometry works out the way it is. So just hold on one second here. Okay, I couldn't find anything physical, but I found this thing online. But this shows, if you look at the screen, this shows a tetrahedral structure. So imagine the central atom in the center being the oxygen. And imagine one of these in the corner. What it shows you is how 4 things will arrange around a central atom in the most spaced out way possible. So because remember that electrons have the same charge, a negative charge. So they're going to try to space themselves out as much as possible. So so you can imagine what happens is that, imagine like 2 of these are hydrogen, like let's say that's a hydrogen, and the other 2 things are the like lone, the pairs of electrons, the unbonded pairs of electrons. So if you take a look at this, you could see that angle right there is not a straight line. It's about 104 degrees, okay? So that's why water molecules have that certain angle. And it's really important because, ends up, you could imagine with these being electrons, right? These 2 right here being electrons, and then these 2 being hydrogens, ions, these end up being positively charged. And these on the other side, this other side, because the lone pairs of electrons are over here, they end up being negatively charged because electrons, have a negative charge. So you end up with, again, a polar molecule that way, where you have one side of the molecule being negative, the other side being positive. So you have to kind of think of this tetrahedral shape. Tetrahedral mean 4 sides, to explain why water molecules have the angle that they do. So anyway, I hope that makes a little bit of sense. And that's why they don't have a straight line structure like for example, carbon dioxide. All right. So moving on to number 11, why is water such a potent molecule capable of dissolving solid rocks? I've said this a million times in class, and I'm sure you remember that water, like I just said, is a polar molecule. And that's why it's so good. One side of it is positively charged, one side of it's pretty strongly negatively charged, and that it makes it so good at pulling apart ionic bonds. And a lot of rocks are ionic bonds, contain ionic bonds. So that's why it's so good at dissolving different solids. Okay, number 12, why do water molecules stick together? What kind of bond is it? So, of course, the H2O molecule in itself, one molecule, right, is bonded together by covalent bonds between the oxygen and hydrogen. However, there are also bonds that are called intermolecular, that bond together the different water molecules. Different water molecules are bonded together by hydrogen bonds, okay? So these are called hydrogen bonds. That's really important. That's going to be on the test big time. I'm writing test instead of bond. Hydrogen bonds, okay? is water a polar molecule? Of course, you know that it is polar, right? We've talked about that a lot of times. That's a really important fact about water. It's definitely going to be on the test, so make sure you know that it's a polar molecule. So what are some properties of water that arise from its polarity? There are really, I covered a lot of different things in the in the lecture about this, but so much stuff. The surface tension, right? That's a function of its polarity. Its ability to dissolve, solids. That's a function of its polarity. It's a you can put like a solvent. It's a universal. Water is often called a universal solvent. It can dissolve all sorts of things, right? It's due to its polarity. Its high heat capacity. Another thing that's due to the polarity is the fact that the solid phase is less dense than the liquid phase, right? So that's why ice, floats on water. Okay, that's due to the hydrogen bond. The latent heat, the high latent heat, that is also due to hydrogen bonding. Okay, you might remember the latent heat of formation for going to, like latent heat of condensation, latent heat of evaporation. You might remember all that. Those are all things. There's so many different, very unique properties of water that are from this process of hydrogen bonding. So, all right, why don't water and oil mix? It's because water is polar, oil is nonpolar. Simple as that. Okay. So please label each of the arrows the names of the two processes that correspond to each phase change that's indicated. So going from ice to water, of course, that's melting. Another word for that, more scientific word, is fusion. Going from water to water vapor and back, that's condensation. Of course, here this is freezing. Condensation, evaporation, right? Now down here, when you skip the liquid phase, you go directly from solid to gas or gas to solid. We call that either sublimation or deposition. Okay, sublimation is when you go from a solid to a gas to a solid. We call that deposition. Okay. Now we also have to know how heat is exchanged in each of these. So when you go from water to a water vapor, so you do evaporation. Okay. When you go from water to a water vapor, that ends up that requires heat from the outside to break the hydrogen bonds. That means it's going to absorb heat from the environment. Okay, so that means it's going to absorb heat, it's going to cool things down. Vice versa, when you have condensation of water is going to release heat. So it ends up heating up the environment. The same kind of analogous thing happens with ice going to water or water going to ice. When ice melts, you have to break hydrogen bonds. That means you have to absorb heat from the atmosphere or from the environment somehow. When you go from water to ice and you freeze, that ends up releasing heat, actually. I know that sounds really ironic, like, wow, when you freeze something, you release heat. Yeah, you do, right? It actually releases heat when you freeze something. So sublimation, deposition is really just the sum total of the two processes of either freezing plus condensation or melting plus evaporation. So the energy exchanges are completely additive, right? So it ends up being the same as if you did each step in the process rather than just skipping the liquid water step. So anyway, what that means is sublimation, going from a solid to a gas. You're breaking a bunch of bonds, right? So that's going to, again, absorb heat, whereas deposition, going directly from a gas to a solid, that's going to release heat into the atmosphere. All right. So what is the difference between temperature and heat, by the way? Temperature tells you it's the average, AVG, that means average velocity that the different molecules and different atoms are vibrating within a substance, okay? So it tells you about vibrational speeds, vibrational velocities, okay? That's different. Of course, there's a relationship, obviously, between temperature and heat. Heat, however, is the amount of energy that is contained in all of those vibrations, okay? So temperature tells you how fast it's vibrating, but heat tells you how much energy is contained in all those vibrations. So there's a difference there. It's an important difference. So, but heat is a type of energy. Temperature is really something in and of itself, but it goes back to velocity of different vibrations. Okay. Now the relationship between those two things, temperature and heat, is really spelled out in a very specific property called heat capacity or specific heat. You're basically same thing. Heat capacity is energy required to change the temperature. Okay. So it tells you how much energy it takes to change the temperature of a substance. All right. Now for water is a freak, as I've often said. It requires a lot of energy to change its temperature. Okay. Now that ends up having a lot of repercussions for the environment and for our Earth and all that, because Earth is going to retain its heat a lot better in like coastal environments or maritime environments that have a lot of water, because if it has a lot of water, it's going to be a lot harder to change the temperature of that area because it takes a lot of energy to change the temperature of water. Okay, so I hope that all makes sense. So we're in the oceans in terms of latitude. Does evaporation outpace precipitation? That's in the tropics. Okay, and that's important because that means, if energy, you have to think of the energy angle to all these things. So if evaporation outpaces precipitation, we get more evaporation. We get that in the tropics, like I said. If we get more evaporation, that means that a lot of energy is being what? It's being absorbed from the environment. Now, where is precipitation outpacing evaporation? That happens in the, of course, the equator. But it also happens at mid-latitudes and also at kind of the higher latitudes. So really what's happening is at the tropics, a lot of heat energy in the tropics is being absorbed by the evaporation, and it's being moved. We'll learn more about this in the very last lecture when we talk about, not the very last lecture, the very last lecture before the test about atmospheric circulation. All that energy is getting moved to another part of the world, okay? Because that precipitation that happens in the mid-latitudes and high latitudes is coming from the tropics, and it's moving with it the energy, okay? So it's a big kind of thermostat that helps to keep the temperatures of Earth sort of moderated so that we don't have temperature extremes in the tropics, and we don't have temperature extremes, cold temperature extremes in mid-latitudes and polar environments, okay? So at what latitude is the ocean releasing heat? What latitude is being released? So I just answered that. So tropics, it's being absorbed. I have released twice, don't I? Absorbed. And then kind of mid-latitudes and higher latitudes, it's being released, okay? So then how is the ocean like a thermostat? I explained that, right? You're taking energy from the tropics where it's really hot, and you're transporting it to higher latitudes and kind of, whether it's mid-latitudes, high mid-latitudes, or polar latitudes, okay? All right, some reasons that water heats up more rapidly, or land heats up more rapidly than in the ocean. So we talked about this in a few different places in this class. For one thing, water has a high heat capacity. So I'll put high heat capacity. It takes a lot of energy to change the temperature of water, right? Another thing is that water is transparent, or maybe translucent. So we'll put transparent here. So that means that when the sun shines on the water, it's not only heating up the top inch, it's heating up about the first 1,000 feet of the ocean. Okay, so it's heating up a lot of the ocean. So that sunlight goes through, of course, the layers and sublayers, and is heating up a much larger part of the area of the ocean than is the land. You know, when the land shines on the land surfaces, the heat and the temperature, the solar radiation doesn't penetrate deep into the earth. It only heats up the top inch or whatever. Okay. Now another thing is that water has a high heat capacity. It's transparent. Water also mixes. So that means that the hot water and the cold water are going to get kind of stirred up, and it's going to mix to lower layers. And also water evaporates. So that evaporation of water is, of course, going to take with it latent heat, right? And it's going to absorb that heat, evaporate, and it's going to help it to keep cool. Okay. All right, now number 25, what is the density of water? It's 1 gram per cc. Make sure you know that. That's the density of pure water. Where is ocean water densest? Ocean water is densest usually in the polar environments. And the reason for that is that, hey, it's cold. Okay, so you know that water density is going to increase with a decreasing temperature. So the colder it is, the denser it is, that dense cold water sinks. Where is it least dense? That's typically at the equator. Okay, the equator you have relatively hot water, so the hot water is going to stay on top, right? And it's going to be it's going to be less dense. So what are some factors that affect water density? There are really two important ones you should know. Like I already said, temperature. Then the other thing is salinity. But definitely temperature is the more powerful of the two. So temperature is more of a determining factor in what the density of ocean water is. Okay. So what are some things that affect ocean water salinity? We actually talked a few things in the class, but there's in the polar environments, ice melting and ice formation. Okay, so ice melting is going to when you melt the ice, remember that ice is relatively pure water. So when you melt sea ice, it's going to dilute the rest of the seawater. So that's going to decrease the salinity, whereas ice formation is going to suck out the pure water, leave the salt behind, and the residual water is more salty. So that's going to increase the salinity. Then you have precipitation and evaporation. Okay, precipitation again is going to dilute the salty water, so that's going to decrease it. Evaporation is going to increase the saltiness. The third thing is runoff from rivers, and runoff is always going to dilute the salt water, because remember that runoff from rivers is always going to be relatively fresh water. All right, what happens to salinity with depth in the tropics and in the equatorial waters, and why does that happen? So if you look at salinity, usually goes down with higher depth. And the reason for that is that the saline water is created at the surface from evaporation. So that happens, if that happens at all, of course it's not going to happen as much in the polar environments because it's colder, you don't have as much evaporation. But another thing is that in the poles, you have to remember that there's no thermocline. So because there's no thermocline, that's a really good, I always say that's a really good sentence you should know in your mind, memorize that, is that the poles, polar environment, there's no thermocline, okay? There's no temperature profile. So as soon as salty water is generated in the polar climate, that salty water just immediately sinks. Now that doesn't happen in the equatorial and tropical waters because you have a thermocline and that salty water stays afloat on top of the ocean and can't sink, because if it tries to move down, not only is it salty, but it's also hot, and hot water doesn't sink, right? So it's kind of buoyed up by the colder waters below. So you end up with a salty water layer on the top of the equatorial and tropical waters. Tropical waters, by the way, are much saltier than equatorial waters. Okay, but anyway, things get less salty as you go down. Now, what happens to salinity with depth at high latitudes? Like I said, it's the opposite. It goes up. It increases. And the reason it increases, like I said, is that there is no thermocline at the poles. So there's no cold water to kind of buoy up and lift up the salty water. So as soon as salty water forms from ice formation, it just sinks right to the bottom, right? Goes straight down. So what do you call that dramatic change in salinity with depth and the near surface water? Of course, that's called the halocline. Make sure you know that. Thermocline is when you have that dramatic change in temperature in the near surface water. Okay. Now, how does the temperature change with depth at the equator and tropics? Very simple and very predictable. The temperature goes down as you go down in depth, and that's just because, there's less sunlight. Remember that the sun is the one that's heating up the water and providing all the energy for the water. That doesn't happen at the poles, though, right? There is no thermocline here, no thermocline in the poles. So at the poles, it's cold at the bottom and it's cold at the top. And remember that if anything freezes, everything's at the same temperature at the poles. It's basically 32 degrees Fahrenheit, 0 degrees Celsius. It's a little bit different than that because it's salt water. The temperature is a little bit depressed, a little bit colder than that. But it's near, let's just say, 32 degrees Fahrenheit, 0 degrees Celsius. If anything cools down below that point, it forms ice, and the ice just immediately rises to the surface. Okay, so it gets separated from the system immediately. Okay, so everything's at the same temperature. There's no thermocline. Now, how does this density change with depth at the poles versus lower latitude waters? Basically, that's called the pycnocline. Okay, pycnocline. There's no pycnocline at the poles. And the reason is because, I'm going to put BC, because there's no thermocline. Okay, whereas at the equator and at the tropical lines, what you find, tropical waters, equatorial waters, you find that the water on top, predictably, the water on top is less dense than the water on the bottom that's colder. And of course, the water on the bottom is colder, so it's more dense and it's at the bottom. You wouldn't expect, right? You're never going to have the opposite where you have denser water on top and less dense water on the bottom. That doesn't happen. Nature doesn't do that, okay? Because that dense water would just immediately sink. But you can have no density profile, right? Like you have in the poles where there's no difference in density. All right, what are the 4 most common ions in sea salt? So moving on to ocean chemistry, those, definitely know those. Those are going to be on the test big time. Sodium chloride, magnesium sulfate, okay? So this is Na plus, Cl minus, Mg2 plus, and SO4 2 minus, okay? What's the percentage of salt on average in the ocean water? It's 3.5%. Average number of grams of salt in a liter of water or a kg of water, that's 35 grams. Another way of thinking about this is 35 per mil. Okay, so know all those different ways of expressing the concentration, average concentration of sea salt in ocean water. 3.5%, 35 grams per kg of water, 35 grams per liter of water, 35 per mil. That's all the same thing, okay? So we put 35 grams per kg or 35 grams per liter, okay? All that means the same thing. It's just different ways of expressing the same number. And I'm sorry that it's confusing, but the fact of the matter is in science, people have preferences for how they express things, and you just end up with all these different ways of saying the same thing twice, okay? So what are 7 other common ions in the seawater? There's a lot of other things. Definitely no potassium and calcium. Those are really first order types things. There's a lot of carbonic acid as well. There's a lot of bromine as well, actually. Bromide, I should say. There's also, besides that, there's also a lot of, boric acid. Let me see. Write that there. There's also fluorine. There's strontium. There's and there's all trace elements too. Well, we don't have to get into that, but so those are some examples of things you could put that. You don't have to know all those, but I would say probably the most important ones to know are carbonic acid, the calcium, and the potassium. Just be aware of those ones especially. Now, where does salt in the seawater come from? Comes from, of course, volcanic outgassing, and that's at the mid-ocean ridges, and it also comes from runoff from rivers. Okay, just like that. Now, what ion's more concentrated in stream water than ocean water? Why is that? If you look at I think I bring it up for you. Let's see here. Just show you this table. You might remember that silicate is more concentrated. Let me just bring it up so you can see it and remind yourself. Oh wait, actually it's from second lecture. Just kind of remind you about this stuff. No, here, this one. Okay, so if you see here, river water has a higher amount of higher percentage of silicate. Actually, this is in terms of percentages, so this isn't really very useful for us. I didn't really want to show you that one. Well, it's okay, but the answer there is silicate. So write that there. And now the reason for that is that silicates are really, I always say, a hot item. It's a really important component for for phytoplankton and other kinds of plankton too in the ocean. And so marine life really uses that up very, very quickly. As soon as silicate enters the ocean from a river runoff, it'll get used up very quickly. Okay. Now, how hot is the water being emitted at mid-ocean ridges? Remember, this goes back to part explaining why mid-ocean ridges release so much salt into the ocean. Because remember, hot water can dissolve rock a lot more easily. So that water is really hot. It's 350 degrees Celsius. And the reason it's able to get so hot without boiling is because of the high pressure at the bottom of the ocean where the mid-ocean ridges are. So what gases are being emitted into the ocean at mid-ocean ridges? There's a lot of different gases. There's H2S, that's hydrogen sulfide. There's also CO2. There's even helium. There's CH4. There's all sorts of gases there. Those gases together, there's fluorine too. Fluorine gas. I'll just put F2 for that. All those gases are collectively called excess volatiles. Okay. All right, now going on to atmospheric circulation. Some of the abundant non-variable gases that are in... Okay, that's fine. Some of the abundant... I'm sorry, I'm just getting a cough drop here. So some of the abundant non-variable gases in our atmosphere. Let me talk a little bit about that. So you have, of course, and in our atmosphere, you have, of course, nitrogen and oxygen, and there happens also to be argon. Okay, nitrogen's about 78%, oxygen's 21%, argon's about 1%. Okay, like that. Now, how does the density of the atmosphere vary with elevation? So it decreases. Okay, so the density of the atmosphere decreases as you go up in elevation, and along with that, the pressure decreases too. So not only air pressure, but also density decrease. So go down with elevation. Why are temperatures normally lower at higher latitudes? Okay. So I'm sorry, I guess I'm kind of skipping around here, it seems like. But temperatures are lower at higher latitudes because I can actually kind of draw this out, and that might be more effective to explain this. But let's say here's the Earth, okay? Let's say here's the poles and the axis, okay? So this is North Pole. The sunlight's coming in like this. So let's say you have a beam of sunlight coming in up here, and you have a beam of sunlight coming in kind of closer to the equator like this. Okay, and you can see that that beam of sunlight is heating up a smaller area, even though the beams are supposed to be about the same width. I'm trying to kind of draw them the same width. This beam is heating up a larger area of the Earth than this beam is. So basically, sunlight coming in at higher latitudes is kind of diluted. It's being spread out over a larger area. So that's why you end up with lower temperatures at higher latitudes. It doesn't have anything to do with like being, closer to the sun or anything like that. Okay. Now, how does density of the atmosphere vary with elevation? So we already did that. I'm sorry. That's number 45. How does air pressure change with elevation? So I already told you that goes down, okay? How does temperature vary with elevation in the troposphere? So temperature goes down as well. So what goes down with elevation? Air pressure, density, and temperature all go down with increasing elevation. There's a reason for all that. So that rate of temperature change with altitude is called a lapse rate. Okay, it gets colder as you go up because of adiabatic cooling. Okay, so you might remember the adiabatic lapse rate and all that stuff. So when a gas depressurizes, it moves up, right? It depressurizes. You get this adiabatic cooling process that cools everything off, okay? All right, now, what is the ITCZ? We talk a little bit about this in lecture, the very last lecture before the test. So the ITCZ is the intertropical convergence zone. And basically it's an area that is similar to the same thing as a subsolar point. It kind of follows the seasonal migration of the subsolar point, north and south. And it's an area where in the tropics, somewhere in the tropics, on average it's around the equator, where the air is going up, okay? So air is converging together and going up like this. Whoop, whoop. And as it goes up, it, of course, depressurizes, it cools adiabatically, reaches the dew point, condenses, and it forms precipitation. So the ITCZ is an area of intense precipitation. It is what is responsible for monsoon seasons. It's what's responsible for like the rainy season that you get in tropical countries. It is also responsible for rainforests of the world and things like that. Okay, why is there a lot of precipitation on the ITCZ? I just explained that. Air is coming together at the ITCZ. It's converging. It moves up. It cools down due to adiabatic cooling. It condenses, and then it precipitates. So it's a kind of global belt of low pressure, global belt of precipitation. It goes around the entire globe. What is the name of the global wind cell in which air rises at the ITCZ, descends at the tropics? That's the Hadley cell. What's the subtropical high? So you know that air rises at the equator, so I'm going to put it here EQ, and it's going to go either north or south, okay? And then it's going to come down at about the tropics, around the tropics, not right on the tropics. Usually it's more like 30 degrees south, 30 degrees north, okay? It's going to come down, and that creates the subtropical high, okay? That's the subtropical high. I talked about that in lecture. And then it comes back and creates the horse latitudes, creates the trade winds, and then the cycle begins again. So that's the Hadley cell, of course, right? That's what's being depicted here. You get the STH coming down at either 30 degrees. It changes seasonally, actually. Texas is sometimes part of the STH at different times of the year. But it comes down right on top of, on average, 30 degrees north and south, close to the tropics, subtropics, and it creates those areas of high pressure along with very dry conditions and very hot conditions. Okay, so why is the ocean saltier at the STH? It's due to increased evaporation. Okay. What are the trade winds? What causes them? I already kind of explained this above, but basically you have the Hadley cell. The air is rising at the equator, at the ITCZ, around the equator. It's going either north or south, and it's coming down at the STH on average around 30 degrees north and south. And from there, it travels back to complete the cell it travels back towards the equator, and that generates the trade winds. Okay. All right, so moving on from there. I'm sorry I'm making all this noise. I'm sucking on this thing, but I just have a little cough still, so I don't want to start coughing instead. But what's the Coriolis force? Coriolis force is a fictive force that directs, and I can maybe say even, what's a good word for it? It alters or changes the direction of a moving fluid away from its straight line path, either to the right or to the left, and it's due to the rotation of the Earth. So this is from rotation of the Earth. Sorry, I'm going to click this here. Okay, so whenever a fluid, whether it's fluid in terms of air, right, so air moving, or water, because we'll see that the Coriolis force also affects ocean currents, you're going to have a movement, a diversion to the right in the northern hemisphere or to the left in the southern hemisphere, depending on, so what hemisphere you're in, you're going to get right or left, okay? So you get a deflection in that. In the northern hemisphere, Coriolis deflects fluid movements to the right, southern hemisphere to the left, okay? So trade winds and westerlies. Trade winds, again, I kind of explained that before, but I do want to explain the westerlies. So after you have the Hadley cell, if you look at the Earth, right, and let's say here's the equator in the center. Okay, that's the equator. You have the air moving up at the ITCZ, and it goes either left or right, or I should say north or south, okay? It comes down at the STH on either side of the equator, either hemisphere. It comes down at the STH. So that's about 30 degrees. 30 degrees. And from there it goes like that, right? And that creates the trade winds. So these winds blowing across the surface here are the trade winds. Now some of that wind also goes this direction, right? So it also goes that direction. That creates, on the other side, you have the trade winds, and on the other side, further to the north or south, so higher latitudes, then you get the westerlies. And these are again blowing from the west towards the east. Okay, whereas the trade winds blow from the east towards the west, at least in the northern hemisphere. All right, so that's all there is for your test. You'll notice I kind of kindly skipped over a lot of the tougher chemistry stuff. So I kind of tried to keep it relatively short for this one, because this is kind of, honestly, I think kind of harder test, because there's the material's a little bit harder. So I kind of restricted this study guide to be kind of more focused on what you really need to know. So anyway, hope that this helps you to prepare for your test. Good luck, and just let me know if there's anything else I could do for you to help you to prepare. Okay? Talk to you next time. Thank you.